All right, we've learned about the binary numbering system, and one thing that hopefully you've noticed that is sometimes binary numbers can be kind of cumbersome to work with. They can be very long. Where we may have a two-digit number like 64. That may be, a very long number for a computer. 1, 2, 4, 8, 16. 1, 2, 4, 8, 16, 32, 64. So you can have very long numbers, and the reason for that is because they only have two symbols. So they have to kind of roll over and make longer numbers faster than we have with 10 symbols. So one of the things that we will use frequently with binary numbers is actually a third numbering system, but it's not that different from binary, so don't worry. It's called the hexadecimal numbering system. Hexadecimal. Now let's kind of piece this word together. You see that deck that we talked about earlier, that's 10. And if you ever have a tool that's a hex-shaped tool that's six-sided, hexadecimal is 16 symbols. Okay? This may seem like a whole new system, but don't worry, it's not that much different from binary, or from decimal for that matter. With 16 symbols, that means we have more symbols than we have in our decimal numbering system, which means the numbers will actually be smaller than our numbers. In other words, 64 may be fewer digits. So here's how hexadecimal works. For the first 10, it's the same ones, dot, 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 8, 9. Okay, so this represents our same 10, but we need 16. So they use A, B, C, D, E, and F. Okay, and if you add it up, that is 16 symbols, which means it would not be uncommon to see an example hexadecimal value of 3A, base 16, or 4D, base 16, or even BF, base 16. Now, you will not see Z4 because Z's do not exist, okay? So you would not see that. But these are all very common hexadecimal values, okay? Now, this is where it's very important to write these 16s because you may see 4-2. What does that mean? If that's base 16, that's one thing, but that's not equal to 42 base 10. Okay? Now, you will not have to convert from hexadecimal to binary, but we will convert from binary to decimal. And let me show you how this works. And this is actually, I think, very straightforward. We're going to, well, before I do that, let me kind of remind you, in binary, these numbers are from 0, 1, 2, 3. I'm not going to write them all out, but 4. That's a 4. I'm hitting the 4. Sorry, I really skipped a few numbers there. Let me go back. My mistake. Okay, 3. Sorry, that should have been only. Sorry. Okay, that's 3. Now we have 4, 5, 6, 7, 8, 9, 10. Now, but notice I went straight through 9 because we now have a symbol. A is equal to, sorry, A should be equal to 10 right here. So where we don't have a symbol, they do have a symbol. So the next one would be 1, 0, 1, 1, 1, I'm sorry, 1, 1, 0, 0. That would be 10, 11, 12. 13, I'm running out of room. I'll write over here 14 would be, and then finally 15. Now, I wrote all that out to show the largest number that you can have with a single hexadecimal digit, these are the hexadecimal digits, in binary are 4 digits. Okay, so notice that F is represented by 4 ones. So that's the largest digit you can have with hexadecimal. And if that doesn't make sense, I can understand it's a little muddy to how I explain that. But here's how this is important. Let's take the number 0, 1, 1, 0, 1, 1, 0, 1. Okay, now let's say you had to work with that number, remember that number, use that number, put that number in a computer. It's got a lot of numbers to memorize. So what we're going to do is we're going to kind of just, in fact, I'm going to change my pen color one more time just because I can. Let's go with a light blue. Okay, so we're going to divide this in groups of 4. Why 4? Because 4 is the largest number of digits that you can have with a hexadecimal number. Divide that in 4. Now, let's convert this back to decimal. We have 1, 2, 4, 8. But don't keep going because this is like a new number. 1, 2, 4, 8. Okay, so let's do the math here. 8, 4, and 1 is 12. That's 13. And that's only 6. So this is the number 6 and 13. But we have symbols for those. Remember, we have individual symbols up to the value 15. Because remember, 0 is a counter, so 0 to 15 is 16. So let me rewrite this a lot more clearly than I did the first time. A is equal to 10. B is equal to 11. C is equal to 12. I'd probably write this little system in your notes. E is 14. And F is 15. Now, if you went to 16, you actually have another column, or another digit, so you wouldn't ever do that. So what was 13? Look at my scale. And here's how I would do these problems. I would write this down. If this was a quiz or a test or in your homework, you will write this down first, then do the problem. Then you just look at your chart here and convert it. 6 is a 6. You don't have to convert 6s. 13 is D, base 16. So this number here is equal to 6D. And that's a much easier number to remember and work with. And you're going to actually see hexadecimal numbers a couple times this year when we get to graphics. They actually use hexadecimal numbers frequently. Even in Microsoft Word, when they work with colors, you'll frequently see these codes. I'm going to do a couple more because that was a little cluttered. So let me do a few more of these. And so this is how a sample homework problem would work. Let's say you have the number 1, 0, 1, 1. I'll do a longer problem. 0, 0, 1, 0, 0, 1, 1, 1. Okay, so that's one number. But we're going to divide, in fact, let me do it in groups of 4, so it's a 1, 1, 1, 1. Okay, so we're going to divide it, divide it, divide it. Now, here's one you can kind of memorize. 4 ones is always 15, which is an F. So we know that one. That's 7, which everything below 10 is the same number as decimal. So that's 7. That's a 2. Again, same rule. There's nothing, 2s are 2s in hexadecimal. We have a 1, 2, 4, and 8. So 8, 2, that's 11. And I erased my chart here, but let's just at least do the first 2. That's all we need. 11 is B. There's your final answer. Don't forget to put base 16. It's probably better to rewrite this close together so you know that's one number. But B27F is a shortcut, and I guess I should have kind of clarified. Hexadecimal values are just shortcuts to decimal. I'm sorry, shortcuts to binary because they translate directly. Every 4 is a letter or a number, but it's 4 and then it's shortcut. Next 4, shortcut. Next 4, shortcut. Next 4 are and a shortcut. So you don't have to ever go into 1, 2, 4, 8, 16, 32, 64, 128. You don't have really large numbers to calculate. The largest number you ever have is a 15, and you can memorize that by saying oh. So you know something like that would be 1, 2, 4, 8. Okay, that's 12. Okay, that's a C. Base 16. So that's some of the largest numbers you have to work with. So it's not that bad of of a division or a problem to calculate. So that's hexadecimal values. I will not be asking you to reverse this process. It is possible by dividing by 16. It gets a little cumbersome, but you will not have to tell me what does F2 in hexadecimal equal to. You will not have to do that kind of problem, but I will give you a binary number, maybe this long, maybe a little smaller, and say what is the hexadecimal value, and you will tell me B27F. And that is the hexadecimal numbering system, which will computers actually don't use, humans use it. That's a shortcut. Computers have no problem with all these digits. That's what they do well. It's humans, when we have to actually interpret these numbers and work with them and write them down and read them back to people, that's when we like working with these numbers. So it's really a shortcut for us humans when we have to work directly with a computer. So that is hexadecimal numbers. Goes from 0 to value 15, and the highest value in hexadecimal is an F.